Hey, it's Zach, and today we're talking about diodes. So enjoy, and don't forget to like, subscribe, and click on the notification button for more electronics videos. A diode is an electronic device that only enables current to flow in one direction. Let's see this visually. In the diagram, conventional current can only flow from the anode to the cathode. If current tries to flow in the opposite direction, it won't be able to do so because the diode will block it. But how does it do this? Let's look at the internal composition of a diode. Before we look at the internal composition of a diode, I would like to make the following disclaimer. For this video, even though diodes can be made of many different materials, we will only be looking at the internal composition of a silicon diode. The reasons for this are that silicon diodes are very common, and by understanding how they work, you will have the foundation to understand how all diodes work. Silicon in this form is not very conductive, but it can become conductive through a process called doping. Doping is a process where the silicon is injected with another element that changes its composition. For something called an N-type material, silicon is doped with elements that have 5 valence electrons, such as phosphorus, that cause it to have extra electrons. For something called a P-type material, silicon is doped with elements that have 3 valence electrons, such as boron, that cause it to have empty spaces where electrons can travel, called holes. A silicon diode consists of a P-type material bonded to an N-type material. When this happens, the two materials form a p-n junction. At this junction, a depletion region is created because some of the electrons from the N-type side will move to occupy the holes in the P-type side, and some of the holes will move to the electron-filled N-type side. This will form a barrier called the depletion region. In this region, a slightly negatively charged area and a slightly positively charged area will form, creating a magnetic field preventing more electrons from flowing. When a voltage source is placed in such a way that the positive end is connected to the P-type material and the negative end is connected to the N-type material, a forward bias is created, allowing the electrons to overcome the depletion region and enable current to flow. When a voltage source's polarity is reversed, the holes are pulled towards the positive and the electrons are pulled towards the negative, causing the depletion region to expand and therefore prevent current from flowing. Before describing silicon diode applications, let's talk about key characteristics all diodes have. The first is their forward bias voltage. This is the voltage required for the diode to overcome its depletion region and allow current to flow. If the voltage at the anode in conventional current flow is less than the rated forward bias voltage, the diode will not allow current to flow even if the current is flowing in the right direction. For silicon diodes, this is typically 0.7 volts. The next characteristic I would like to talk about is the reverse bias, or breakdown voltage. When a diode is normally biased, it will conduct in one direction. When the diode is reverse biased, current will not flow until the breakdown voltage is reached. Usually it is significantly higher than the forward bias voltage. When this occurs, the diode is destroyed with the exception of a Zener diode that is designed to operate in a back bias condition. Zener diodes will be discussed later on in this presentation. The last characteristic I would like to discuss is the maximum forward current. Diodes have a limit to how much current they can handle before they are destroyed. That's why you'll often see light-emitting diodes, more commonly known as LEDs, in series with a resistor. The resistor will reduce the current flow into the LED, preventing it from being destroyed. For more details about why the resistor will reduce the current flow, check out my video about resistors. Now let's discuss a few silicon diode applications. The first major application I would like to discuss is its ability to help turn alternating or AC voltage into direct or DC voltage. This ability is vital because in the United States and many other countries, voltage from the power company is delivered in AC. However, Many devices in your house, such as your cell phone charger and your TV, use this type of circuit to convert AC voltage into usable DC voltage. Diodes convert AC voltage to DC voltage using half and full wave rectifier circuits. In a half-wave rectifier circuit, the transformer takes the high AC voltage and reduces it to a voltage level that can be used in DC circuits. Then the diode allows a positive part of the AC sine wave through while blocking the negative voltage waveform. Then the capacitor smooths out the waveform to make it usable for devices that use DC voltage. For more information on how capacitors do this, check out my video on how capacitors work. Full-wave rectifiers work in a similar way, except that they convert the negative part of the waveform into a positive one. The advantage to this type of rectifier is that the capacitor is able to recharge twice as often as the capacitor in the half-wave rectifier. This enables the power supply to handle larger loads. The disadvantage to this type of rectifier is that it costs more to manufacture and is more difficult to accommodate on smaller circuit boards. The other major application for silicon diodes is to protect components from back electromotive force, or back EMF. Back EMF occurs when current flowing through an inductor, such as a DC relay or motor, is suddenly switched off. When this happens, the collapsing magnetic field will generate a high voltage spike in the inductor's coils, damaging the inductor or mechanical contacts. The damage to the inductor can be avoided by placing a diode in parallel with it. The diode provides a safe path for the back EMF to travel that will prevent the relay from being damaged. The next type of diode I would like to discuss is the Zener diode. While the Zener diode has the same forward bias voltage as a silicon diode, what makes it unique is that it's designed to operate in reverse bias. To explain how this operates, let's take a look at the following circuit. In this circuit, there's a voltage source of 14 volts, a resistor rated for 1 kilo ohm, and a Zener diode with a back bias rating of 12 volts. Per Kirchhoff's voltage law, the voltage into the system must equal the total voltage drops in the circuit. In this circuit, 14 volts are put into the system and 12 volts are required to actuate the Zener diode. Therefore, the voltage across the resistor is 2 volts. What makes a Zener diode so unique is that even if the voltage source increases, the voltage right before the Zener diode will always be 12 volts. This means that the Zener diode can be used as a voltage regulator. Let's see an actual voltage regulator circuit to see this principle in action. In the voltage regulator circuit, the voltage right before the load will always equal or be less than the Zener breakdown voltage and never greater regardless of the input voltage. A light-emitting diode, or LED, is a diode that emits light when current flows through it. Unlike silicon diodes that are made of specific elements, LEDs are made up of different elements based on the color light it emits. For example, a red LED is made up of different materials than a green LED. The general principle to be aware of is that LEDs that emit cool colors, such as green, blue, and purple, have larger forward bias voltage ratings than warm colors such as red, orange, and yellow. Therefore, they require more voltage to operate. LEDs, besides looking cool, make great indicators in circuits. For example, in this circuit, a 12-volt power supply is connected to a fuse in parallel with a resistor and an LED. If the power supply experiences a voltage spike, the fuse will blow, preventing the circuit from being damaged. The current that used to flow through the fuse will now be reduced significantly by the resistor and then flow through the LED. At this point, the LED will light, letting the engineer know that the fuse blew and the circuit needs to be looked at. Today we discussed how diodes work, their internal composition, and some applications of silicon, Zener, and light-emitting diodes. Hey everyone! I hope you enjoyed this video, and don't forget to like, subscribe, and click on the notification button for more electronics videos.